Everyone, I'm Nathan Elwailly, and this is my Physics 130 final project. I will be talking about taking powers of matrices. I'll talk about evaluating functions of matrices, and finally, as an example, I will show how this is relevant to discrete dynamic systems. Taking powers of matrices allows us to do several things with matrices that can be done with scalars, such as evaluating nonlinear functions of the matrix or other odd functions. An example I'll show is a class of problems called discrete dynamic systems that we can explore once with the powers of matrices. So taking powers of matrices. In class we saw it's straightforward to take powers of square matrices, such as a to the n, where n is a scalar. One method of making this easier is by diagonalizing the matrix. So P, D, P inverse, where P is the eigenvector matrix and D is the diagonal matrix. So if we raise a to the power of n, we simply have P, D, P inverse to the n. And as you can see, all the p's will cancel except for the first and last, and you get P, D to the n, P inverse. Once we can evaluate powers of matrices, we can take odd functions of matrices. Any function that can be represented as a Taylor expansion. The reason of this behind this is that Taylor expansion is simply a sum of powers. So any elements that we can take the power of, we can plug into a Taylor expansion. The obvious example is a scalar, so e to the power of a scalar is 1 plus set scalar over 1 factorial, etc. But we can also use a matrix. E to the power of a matrix is 1 plus the matrix over 1 factorial plus the matrix squared over 2 factorial plus a3 over 3 factorial, etc. The one caveat, of course, is that the Taylor expansion has to converge, which it doesn't always, which is also the case for scalars. Discrete dynamic systems are another case where taking powers of A is useful. An example here is the population change of coyotes and rabbits from year to year. For example, if you have R is the number of rabbits and C is the number of coyotes, then we can represent the number of rabbits in the n plus 1th year as as some number slightly larger than 1 times the rabbit population of the previous year minus the loss of rabbits due to being eaten by coyotes. And similar logic applies to coyotes. The n plus 1th population of coyotes is some background increase, which is less than 1, independent of rabbits, plus the increase due to them eating rabbits. And without rabbits, their population will go down. This whole thing can be represented in a matrix form. If you have C of n plus 1 and R of n plus 1, this can be represented as a vector, and similar for C of n and R of n. So you have some matrix times C of n R of n vector equals the C of n plus 1 and R of n plus 1 vector. This matrix can be applied multiple times to get to the next year, and then the next year, and then the next year. So you have, if you have the x sub 0, if you have the x plus 0 population, then you can multiply by the matrix n times to get the nth population matrix, the population of year n. And as usual, we can, of course, diagonalize that to get P, D to the n, P inverse times the original gives the nth population. We can place this on a graph as well. So for example, on this graph of rabbits over coyotes, this you can have, for example, if the number of coyotes is relatively large and the number of rabbits is also relatively large, then the population will go down slightly over the years before stabilizing. But if you have less rabbits but the same amount of coyotes, and this then the coyote population will go down more drastically before stabilizing, as expected. And finally, if you have very few rabbits, then the ecosystem basically collapses before, again, stabilizing. As an extreme example, if you have a whole lot of coyotes, then the number of rabbits will go to 0, and then coyotes will eventually go extinct. Alright, thank you for watching my video. These are the references.